Hello class, I hope you are having a wonderful day. Today I would like to take a look at the heat transfer assignment, and what we're going to need is the heat loss and gain assignment sheet, and we will also need the R value densities chart to complete the assignment. So what we're going to do is ultimately calculate the amount of energy loss we have from our shed. Okay, so what we're going to do is we are going to identify each R value of the material in each wall. We're going to identify the R value in the ceiling or the roof, and then the double doors and the windows. And so what we're going to do is we are going to transfer the total R value from each wall, double door, window, and the roof. We are going to place that value in the table that I've drawn on the board here, and then we are going to calculate the transmission load through each wall. We are going to sum those values together so we can calculate the total transmission load. And we're going to have units in British thermal units per hour, or BTUs per hour. So let's go ahead and get started. On page 2 of your assignment, we have table 1, and so I've written the information right here for table 1. So the first material that we have in our wall is the 1/2 inch OSB, that stands for oriented strand board, and it is the low density type. So what we're going to do is we are going to take a look at the R value densities chart that I gave you. So let's go ahead and look up oriented strand board low density. It's in the material section, and it says that it has an R value per inch of 1.41. Now if you notice here, it's given us a thickness dimension of 1/2 inch. So 1.41 divided by 2 is going to be 0.705. Okay, the inside air film. Okay, we're going to have to look that up. It's on the first page, and it's the first row in the materials section. We have an R value per unit of 0.68. Next, we have the R11 Bat Insulation, and insulation is usually named by its R value. So when it says R11 Bat Insulation, the R value is 11. Okay, next up we have 1/2 inch oriented strand board low density, and so this is the same thing, the same value that we have here, 0.705. Next we have a vapor barrier. I believe this is on page 2. Yes, it's on page 2 under the insulation section, and it is the last row. It says the R value per unit is 0. So that is absolutely worthless when we're talking about transmission load. Next, we have 3/4 inch by 10 inch wood bevel siding. So this is located under the siding section at the bottom of the R value densities chart. So in the bottom section, it has an R value per unit of 1.05. Now, what we're going to do here, that we have all of the material R values, is we're just going to sum this column. After we do that, we are going to transfer this value over here to the R value, the total R value for the west wall. Now, in this table, the utility shed wall, this is for all 4 walls, the north, east, south, and the west wall. But let's go ahead and sum these values here. And we get 14.14. All right, so I'm going to use a different color of marker here. Let me use something a little bit darker. Here, I'll use this. Maybe that's a little bit easier to see. Okay, so here we have a value of 14.14, and this value is good for all 4 of the utility shed walls. So now that we have this value, let's go ahead and transfer the value into table 5. So the total R value for our west wall, 14.14, and that's going to be the same for the east, north, and the south wall. And this east wall is excluding the windows, but we're going to look up the value for the single glazed windows in just a minute. So we have 14.14. Okay. All right. Now let's move on to the ceiling and the roof. So we have asphalt shingles. So let's go to the roofing section in our R values density chart. The asphalt shingles have an R value per unit of 0.44. Now let's look at roof felt. That's 0.06. 1/2 inch OSB, this is our oriented strand board. Well, we have this value, so 0.705. Then we have R11 Bat Insulation. Remember that we're going to identify the R value with its name. It's named after its R value, so this is 19. The inside air film, we have that at 0.68. And then the 1/2 inch gypsum wall board. So what let's do is take a look under the first section in your materials section. It says gypsum wallboard or drywall. R value per inch is 0.90. So we're only looking at 1/2 inch. So half of 0.9 is going to be 0.45. And now we need to add those values together, okay? And I get 21.335. Okay, so I'm going to transfer this value over here to the total R value for the ceiling and roof. So 21.335. Next, let's take a look at the double doors. So what we're going to do, go back to the R value densities chart, and we're looking at the doors without glass. I believe that's on page 2. The back of the first page. So it's under the section Common Rules of Thumb. It says doors without glass in the last row. It is 1.67. And then the total R value is 1.67, so we're just going to transfer that value down. Now we're going to write that value in the R total column for the double door, 1.67, which is very low. That is not a good R value, okay? Next, we have the windows. So let's take a look at the single glazed windows. This is in the Common Rules of Thumb on the back of page 1. It says the R value is 0.88. Going to transfer that value there. And so for the total R value column for the windows, we have 0.88. Okay? All right, so what I want to take a look at now is some of the important information that was given to us on the first page of our assignment. So the desired inside temperature is 70 degrees Fahrenheit, and the outside temperature is 9 degrees Fahrenheit. Well, whenever we calculate transmission load, we know that we are required to have the temperature difference. So, delta T here is going to be 70 degrees Fahrenheit minus 9 degrees Fahrenheit. So this is going to give us 61 degrees Fahrenheit temperature difference. So 61 degrees F. Also, we have single glazed windows. So we looked up the R value for the windows, and they are 2 foot in width, 4 foot in height, and we have 2 of those, okay? We also have one double door that is 6 foot in width and 7 foot in height, okay? So our delta T, 61 degrees Fahrenheit. Right here, it's delta T will be the same for the entire column. So 61 degrees Fahrenheit. Let's go ahead and write that value for the entire column. Okay. All right, so now what I want to do is we are going to have to calculate U factors for each of the walls, the ceiling, the double door, and the windows, and then we're going to have to calculate the area under consideration for each surface. Okay, so what I'm going to do now is erase table 1, 2, 3, and 4. I'm going to leave table 5 up, so we'll always be able to look at it, and we can do calculations just next to the table here. Okay, so let's take a look at the U factor, okay? So the U factor is the coefficient of heat conductivity. Here, let me just write that down. We have U factor. This is the coefficient of heat conductivity. And the equation is 1 divided by the total R value for the surface, okay? And so R total is equal to R sub 1 plus R sub 2 plus dot 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 plus R sub n. Now, remember when we talked about this, don't let this equation confuse you with all of these R's and then the subscript n. The subscript n represents the total number of materials that you are adding together to calculate the total R value. So, for example, in the wall, when we calculated that to be 14.14, I believe there were 6 or 7 items in there, and that's table 1. So it would be R1 plus R2 plus R3 all the way through R sub 7, okay? And we already have this R total value for all of our surfaces. So let's take a look at the U factor for the west wall, okay? I'm going to say U factor is equal to 1 divided by 14.14, and our units for total R value are feet squared, hour, degree Fahrenheit per British thermal unit, okay? And so the U factor is just the inverse of the R value. Now, not only are we going to take the inverse of the numerical value, we're going to take the inverse of the unit value as well. So our units are going to be the inverse of this, okay? So I have 1 divided by 14.14. This is going to give us 0.070721. And whenever we calculate U factor, we're required to truncate at the thousandths place, or to the thousandths place. So what we're going to do is we are going to keep the value in the thousandths place, and we're going to drop everything else, okay? So my value is 0.070, and our units here are BTUs per foot squared hour degree Fahrenheit, okay? What we want to do is transfer our calculated value for U factor into table 5. So U factor for the west wall is 0.070. Well, let's take a look at the total R value. It's the same for our 4 walls. So let's go ahead and, since the total R value is the same, we're going to get the same answer for the U factor. So for our 4 walls, 0.070. Okay? Now let's take a look at the U factor for the ceiling and the roof here. So we have 1 divided by 21.335. And taking a look at our units, we're going to have foot squared hour degree Fahrenheit per BTU. So 1 divided by 21.335. This is going to give me 0.046871. Well, we're going to truncate, and we're only going to quote to the thousandths place. So we're going to say it's 0.046. Okay, next we have the double door. So the double door is 1 divided by 1.67. This gives me 0.5988. We're going to truncate. We're going to go to the thousandths place. So 0.598. And then we have the windows with a very low R value. So we're going to be losing a lot of energy with an R value that low. So we have 1 divided by 0.88. Okay, this is 1.136364, and the value goes on. So we're going to quote it to the thousandths place, 1.136. Okay. So now what we need to do is calculate the area of each surface. So we have our 4 walls, the ceiling, the doors, and the windows, okay? So what we need to do is we need to look on the last page of our assignment at the plans, at the shed plan. So there are the 4 elevations, there's a floor plan, there is an isometric view. So right here, turn to this page here. Okay, so let's calculate the area of the west wall first. Okay, so the west wall elevation is in the upper right-hand corner. We have an overall height of 8 feet. And we have an overall width. Now, the overall width dimension is not provided in the west elevation. It's provided in the floor plan view in the lower left-hand corner. And the overall dimension is 16 feet 0 inches. So we have something that looks like that. So our area is going to be 16 feet times 8 feet, and we get 128 square feet. Next, let's take a look at the east wall. Okay, on the east wall, we need to take a look at the elevation in our plans. In the upper left-hand corner, we have the east wall with 2 windows, and it says that our windows are 2 foot by 4 foot, so that's 2 foot, 4 foot, and we have 2 of them. And our overall dimensions are 8 foot and then 16 foot. So we know the total area here of our 18 by 16 is 128 square feet, but we're required to subtract the windows here. So 4 times 2, we have 8 square feet, and we have 2 windows, so that's going to give us 16 square feet. So 128 feet minus 16 square feet is going to be 112 square feet. Okay, next we need the area of the north wall. Okay, in an elevation view, the north, we have something that looks like this. So we need to calculate this entire surface here. Okay, so it tells us that up to the roof line here is 8 foot, and then this is 12 foot, but we still have this business on top here. So the overall height of the roof is 10 foot 4 1/2 inches. Okay, so we know that this right here is 6 foot, and we need this dimension here. Okay, we know that we have a triangle up here. The area is going to be 1/2 base times height. Okay, so 8 times 12, I believe that's 96. Yes, okay, this is 96 square feet. And then what I want to do right here, this is 4 1/2 inches. I want to convert this into feet, so we have units of feet in the y direction and feet in the x direction here. So I have 4 1/2 inches, which is 4.5 inches. We're going to do some dimensional analysis to convert this into units of feet. We know that there are 12 inches in 1 foot. So this is going to give us 4.5 divided by 12, 0.375. So that means the height, I've labeled this with a star here, the height of this is going to be 2.375 feet. So 2.375 feet, okay? And so what we have is 2.375 feet times 12 feet, and we know that area of a triangle is 1/2 base times height, so that's going to be 1/2 times the base of 12 feet times the height of 2.375 feet, okay? And that is going to give me 14.25. So just this area is 14.25 square feet, and we are going to add it to this section of our surface, which is 96. So plus 96, 110.25 square feet. Okay, now let's take a look at the south wall. Okay, so let's look at our plans. The south wall in our elevation. So this is our door. Okay, and so the south elevation is very similar to the north elevation because all of the dimensions are the same, except we're going to have to subtract the area for the door. Okay, so I have the north wall was 110.25. square feet. And we're going to subtract the area of the door. So our door is 6 by 7, so 6 foot in width, 7 foot in height. And so that's going to be 42 square feet. So we're going to subtract 42. So 110.25 minus 42, that's going to give me 68.25. Okay. Next, we need to take a look at the ceiling and the roof. So, okay, we know this dimension here is 12 feet, and we calculated the height here from this 8 foot. We have 2.375 feet. We know half of that here is 6. So we can use the Pythagorean theorem to calculate this hypotenuse length here. And if we were looking at the roof from an angle like this, we would have this, okay? And so I'm going to label this as the dimension star, okay? So in my view that I'm looking at this, we have that, okay? So we need to know that dimension first. So we know 6 squared is 36, so 36 plus 2.375 squared is going to be 41.64, and we're going to take the square root of that, and that's going to give us 6.452 feet. Okay, and now we need, so from this view it would be the depth, but with the picture that I've drawn right here it would be the width of my rectangle, okay? Now we're not concerned about the overhang of the roof. It's only the surface that heat can come through at the top of, so on the inside, the heat that can rise to the inside of the shed, and we're going to lose that energy through the roof. So let's take a look at our plans again, and we are going to have a depth of 16 feet. Okay, and so we have an overhang on our roof that is 1 foot, and we are not going to use the overhang. So with the overhang, the overall dimension, depth dimension, would be 18. There's a 1 foot overhang on the front and the back. We're not using that. So let's calculate the area there. That's going to be 6.452 times 16. That gives us 103.24 square feet. But we have 2 of these. We have this surface on the right side, and then we have this surface. So I'm going to multiply that by 2, so 206.49. And that's going to be in units of square feet. So we have the double door. The double door had an area of 42 square feet. And then we have the windows, and remember it told us that we had 2 windows and they were 2 feet in width, 4 feet in height, so 8 times 2 is 16. So we have 16. Okay. Now what we're going to do is calculate the transmission load for each surface, and then we are going to add all of those values to calculate our total transmission load. And that's going to be in units of BTUs per hour. So that is how much energy we're going to lose in the form of heat from our shed. Okay, so let's start with the west wall here. We're going to use our equation, transmission load is equal to Q prime times the area under consideration times our U factor, which is our coefficient of heat conductivity, and then delta T, our temperature difference between the surfaces. Okay, so the area is 100 area of the west wall, 128 square feet. Our U factor, 70 thousandths, and we're going to have units of BTUs per foot squared, hour, degree Fahrenheit, multiplied by a temperature difference of 61 degrees Fahrenheit. So let's go ahead and calculate this value. Let's talk about the calculated value first. So 128 times 0.07 times 61 gives me 546.56. Now let's take a look at units here. So right here we have foot squared, where algebraically we could just write this as foot squared over 1. That's understood. And we're multiplying it by BTUs per foot squared, hour, degree Fahrenheit. So in my numerator here, I have a foot squared, and in my denominator, I have foot squared here. We know that that can cancel. Over here, for our temperature difference, we have degrees Fahrenheit, and this is degrees Fahrenheit over 1. So I have degree Fahrenheit in the numerator here. I have degree Fahrenheit in the denominator here. That will cancel and leave us with units of BTUs per hour. So our numerical value is 546.56, and I'll go ahead and write the units of BTUs per hour. So that means through the west wall, we are losing 546.56 BTUs every hour. Okay? So let's continue on. Let's take a look at the east wall here. So area is 112 square feet times the U factor of 0.070. Okay, so 112 times 0.07 times 61, I have 478.24. Next, let's look at the north wall. The north wall has an area of 110.25 square feet. And we are going to have a U factor of 0.070. We'll multiply by 61 degrees Fahrenheit. Okay. Let's calculate this value here. It's going to be 4.27 BTUs per foot squared hour. Here we can come up with an algorithm here when we have the same U factor and delta T. So we can use this guy and multiply it by the area of our remaining walls. Okay? So 110.25 times 4.27. This will give me 470.76. Okay, now let's take a look at the south wall. Our area for the south wall is 68.25 square feet. And we are going to use the product of the U factor and the temperature difference, so we've created an algorithm here. So 68.25 times 4.27. That's going to give me 291.42. Okay, and then let's take a look at the ceiling. Okay, so now that we have a different U factor for the ceiling, we're not allowed to use this value that we've calculated for our algorithm here. So let's get rid of that. Now we're still using our equation Q prime equals AU delta T. So the area for the ceiling is 206.49 square feet. We're going to multiply by the U factor for the ceiling, which is 0.046. And then 61 degrees Fahrenheit. And we get 579.41. Next, our double door. So the area of the double door is 42 square feet. The U factor, 0.598. Times 61 degrees Fahrenheit. I get 1,532.07. Wow, that is a massive amount of energy loss compared to energy loss through our other surfaces. So that is not good. We're losing a lot of BTUs per hour out of the double doors. Okay? And our last surface is going to be the windows. So the area of the windows is 16 square feet multiplied by our U factor, which is 1.136. And we're going to multiply that by our temperature difference of 61 degrees. And we get 1,108.736. And that is BTUs per hour. So now what we need to do is sum this column for transmission load to calculate the total transmission load. And remember, this value is going to tell us how many BTUs per hour that we're losing, okay? Oops. Okay, so let's sum these 7 values here. Yeah, 7 values. And I get 5,007.2. And we have BTUs per hour. Okay, so looking at our table here, it looks like the double doors, this is our culprit here. The double doors are definitely causing us to lose the most amount of heat, most amount of energy. Okay, and then it looks like it's it's the windows, okay? All right, so I hope this video has helped you. If you have any additional questions, please give me a call or send me a message. I hope you have a wonderful day.